could you solve this? Yeah, by inverses you could solve it, right? Could you solve this? Yeah, by inverses, maybe if I made it cleaner, actually that's not even possible. Sorry, that has no solution. But if I did something like this, that's doable too, also by inverses, right? Okay, now consider this question. What if instead of all these 6's, I said, what about sine of 2x equals natural log of x minus 2? Now, then it's not algebra as much because I can do the inverse to this side and it's fine and it makes this side great, but it also makes a mess of this side. And so no matter what inverse algebra you do, one side is betrayed and it gets worse, not better. And so there's really no way around it. The way that this would have been solved before the calculus would have been the bisection method. So take a trip back with me 400 years back. Actually, let's make it 500 years back to talk about student your age, 500 years ago, how they would have solved. Now, that one's pretty hairy to learn from. So I'm going to start with this cube. Now, this cube, we know sometimes a cube has nice answers, but sometimes they have really ugly answers, yeah? This one I can assure you has really ugly answers. Now, they would have, I'm going to draw this well. Actually, I wish I would have had this on this slide. Okay, there was only one root, wasn't there? Darn it. Sorry. Hang on one with me. I wish I just want to make a small modification to this. I wouldn't want the graph on this page. So, okay, sorry, real quick. Okay, my bad. I'll prove, Waller. All right, so check this out. They would have started by playing with integers and saying, well, what's close? That's a shame. At 2, if you plug 2 in, that would be -1. That would take you practically no time to find, yeah? They can also plug in f at 3, and if you did, you'd get 5, and that would take you no time to find. Now, what would that tell you? If you went from -1 to 5, and you're looking for a 0, you would know it must have been between x of 2, between x of 2 and x of 3. So it's 2 point something. Do you agree? Okay. Now, if they wanted more precision than that, they would have bisected. And they would have said, all right, I know it's between 2 and 3. Now I'm going to go to the midpoint of that and see which side. Now, they didn't obviously have the graph to look at, so they're working from the equation. I could then plug in 2.5 and see what that equals, and it is 7/8. Now, if they knew that f at 2 was -1, f at 3 was +5, and f at 5 has is 7/8, then that just cut the region in half, and now we know it's between 2 and 5/2. So it must be between 2 and 2.5. Now, if I wanted more precision, I could then bisect that. So I would, what would I next try? I know it's between 2 and 2.5, and if I wanted to bisect that region, I would use 9/4, or 2 1/4. Now, if I use 2 1/4, I wish I had this in my calculator. I wish I remembered what this equals. Let's say, for the sake of time being, that it's -0.1. Now they know an even smaller region. It would have to be between 9/4 and 5/2. So they could go with more precision and go to the 8s and so on. And they could get closer and closer and closer. Now, that would take a while, especially the bigger the fraction denominator, the worse this would get. So it would be a pretty ugly. That's the way it was done for thousands of years, the bisection method. When Newton came along, he's got this calculus going on, and years later, then he's starting to think, wow, this can be really applied in a lot of ways. This is how he applied his calculus to this age-old problem. And it was by tangent lines. So he took the cube, or the equation, and said, well, I know that I could draw a tangent line at one of the good points. Now, it doesn't matter which one, but let's say I used 2. Now, if I drew a tangent line at 2, then it would look something like that, yeah? You agree? Okay. Now, you might then say, all right, great tangent line. Why? Well, what's easier to solve? A cube equation or a linear equation? Obviously linear. We could write the tangent line and then find where, instead of the cube equaling 0, we could say, where does the tangent line equal 0? Because they're doggone close. So that's what we're going to do. We're going to make a tangent line at x equal 2. If the x initial is 2, the y initial is what? Maybe, did we already do that? We had that on the previous. Can you just tell me what that was? 2, -1? Okay, it was -1, right? That was the y value we had from the previous work, 2, -1. The slope is y prime at 2, 3x squared minus 6x plus 2 at 2. The slope is maybe 12 minus 12 plus 2, or 2. So our tangent line is y plus 1 equals 2 times the quantity x minus 2. Now the whole goal is not to get a tangent line, but to get a tangent line and then trace it back to where it crossed the axis, because the zeros are pretty close. So now you want to find the 0 of the tangent line. Where does that 0 go? For x or y? X. X. Tell me, at this point, do you know x or do you know y? Y. You know it's crossing the x-axis. You know y is 0. What you don't know is the x. So you're setting y equal to 0. So 0 plus 1 equals 2 times x minus 2. And you want to go back and say, all right, what's the x that makes that? So the x is, divide by 2, add 2, and so x is 5 halves, or 2 1/2. Okay. Now that's fine. It's a good estimate. But the beauty of Newton's method isn't that you stop there, right? The beauty of Newton's method is that you do it again, but at a new point. That 5 halves, we assume, is closer to the 0. So if we did this tangent line process again, but instead of at 2, we're going to go use 5 halves, go up to the curve, and do a tangent line at that point. Now, if you do a tangent line at that point, then it's really close to the true 0 if you trace back. That's doggone close. Now, that's called the second iteration. This is so tight here that I gave you a zoomed in look here. Here's 2 1/2. Our original tangent line, our first tangent line, was here. Right? Now the idea is that we see where that tangent line is 0 and go back up to the curve at that new x and make a new tangent line there. And the idea is that the 0 of the second is even closer to the true 0 of the cube. Okay? Now, it's not too painstaking to do this by hand, and Newton most definitely did it by hand, but we'll use our calculator. I'll pause here and say the calculator. When you find the zeros to something like this, your calculator can find those zeros, right? I mean, you punch it in your calculator, you do the zero function, and it finds the answer. How does it do that? Right there. That's how it does. Okay? So, it's not programmed. I mean, as Ms. Cannon says, which I totally agree with, the calculator knows how to do 4 things. What are they? Add, subtract, multiply, and divide. Anything else it does is just a combination of add, subtract, multiply, and divide. It's a four-function calculator plus some. Okay? Everything it can do has been programmed into it by mathematicians or by math people to do those things, including by Newton's method. All right, so it finds the zeros, but technically it's just a good estimate. It's actually an irrational number. It goes forever. It doesn't repeat, so we're finding a good estimate. That's Newton's method. So, calculator. Here we go, by calculator. If you would, please pick up thy calculator and clear out your sky. I'm going to clear this out real quick. Okay, now, we first of all want the function in. Call it x cubed. I can't remember what it is. It's x cubed. Oh, sorry, minus 3x squared. Plus 2x? Minus 1, thank you. Okay, it's 1. Okay, now all that's great. Now you're also going to need the derivative. So in y2 or f2, whatever kind of calculator you have, would you also put the derivative? 3x squared, I'll explain why in a second, minus 6x plus 2. Do I have that derivative right? Yes. Okay, you with me? Okay, cool. I guess if you have trouble taking the derivative of a polynomial.
Yeah, it's like super hard.
Yes, it is. Polynomial is really hard to use. Okay, so here we go. We're going to do this one more time numerically, and then we're going to analyze the pattern to get the formula or the method itself, all right? So we're going to start. We started with x initial, y initial was 2, 5, 2, negative 1, right? Mm-hmm. Our first iteration we just did by hand was that when x was 5 halves, the new y we got was, oh no. I'm sorry, just a second. Our first guess at the 0, I wrote that wrong. We don't really care about the y. The y's we know are supposed to be 0. Okay, sorry. The first guess of the x was 2. What the heck? Yeah? The next guess we did after our Newton's method, our tangent line tracing back, we got 5 halves, right? So now we're going to find our second iteration. If we trace this green tangent line back, what's our new estimate? So now, let's start with the point. We're doing a tangent line at our new point, 5 halves, yeah? So we need a point, 5 halves, and would you please put 5 halves into the function to find the y that goes with it? F 2.5. The original function, not the derivative. And you get maybe 0.875, yeah? Do you agree? I don't care fraction or decimal. We'll use a bit of a mixture, which my algebra kids would freak out at. Are you with me so far? Would you also find the slope? The slope is f prime at 5 halves. So that would be f2, or y2 if you have an 84 at 2.5. Did you get 5.75 there? Okay. Not quite sure I gave enough room. All right. Now, with that, we could write our tangent line equation. Our tangent line equation is y minus 0.875 equals 5.75 times x minus 2.5. Do you agree with my tangent line equation? Okay. Now we've got that tangent line equation because we wanted to trace it back to when it crossed the axis. So now what do I want to do? Put in a 0 for y. Where does this equal 0? Well, you put in a 0 for y, and I get something like, if I solve that for the x at which this comes out to be 0, I'd say x is negative 0.875 divided by 5.75 plus 2.5. Yeah? Negative 0.875. Oh, shucks. Negative. Oh, shoot. Never mind. Negative. I guess it won't let me type that. 0.875 divided by, what was it? 5.75? And then plus 2.5? 2.3478-ish. Do you agree? Did you get that? Okay. Now, as far as what number x that is, what number estimate of x is that? X initial is 2. X1 we did by hand. It was 5/2. No, that's x2. It's the second iteration of this process, second time through this process. It's a pretty good version. We could do this product or this idea again. I could say the green line is here. I could trace up to the curve and do another tangent line there, and I would get even closer. That would be 3 iterations. All right. Now, in terms of generalizing this to the formula, let's talk about this so we can generalize, shall we? The first thing we did was to choose an initial guess, x initial, y initial. We'll talk more about choosing that later. There is some leeway in some cases, but in some points, some questions I will say start here so we all end at the same value or estimate. You write a tangent line equation to that point. Say, I also use function notation here. When I write a tangent line equation to that point, wouldn't that be y minus the f value at the point times the slope, which is f prime at the original point, times x minus the original x, yeah? Generally speaking. Cool? Right? We then want to define where the tangent line crosses the x-axis. So then what do we do after we had our tangent? We plug in y of 0. 0 minus f at x initial equals f prime at x initial, x minus x initial. And our goal was to find the x at which the 0 happens. So we solve for x. Solve for x. We get something like, now if I solve this for x, I would divide f prime over. So I would have negative f x initial divided by f prime x initial. And then I would move x initial. You agree I divided it. Now in terms of what I get then, that is my next x, x1. x1 is x initial minus the undoing of the tangent line. What about a second iteration? x2, without all that work, would be x1 minus f at x1 over f prime at x1. And if I wanted to go very general, then the nth iteration, the nth iteration, or the nth time we went through the process, is x to the n minus 1, the one before it, minus f at that point over the derivative. All right, so that's actually Newton's method. This finds zeros of an equation. All right, that'll be important. To find zeros, you need to understand how it's used because it won't always be all set up for you, pretty princess. All right, imagine that if I wanted to estimate the solution to x to the 4th plus x to the 3rd minus 3 with one iteration. That is not clean. It's not a nice integer number, nor is it even a rational number. It's ugly. So if we were to solve this, the first thing we do is take a guess. What's an initial guess or a seed value? 1. 1's not bad. Do you agree 1's pretty close to making a 0, pretty close to making a 2. 2 minus 3 is negative 1. It's almost there. So let's go with x equal 1. That's our initial x. Now, we then say, by Newton's method, Now, Newton's method then involves this whole tangent line idea streamlined to just a formula. We're not going to write the tangent line, solve the tangent line. We're going to just go straight to the Newton's method. So x1 is x initial minus f at x initial over f prime at x initial. That's the formula. Now we're going to substitute. What is x initial? 1. Another person next to you might have chosen 2, and that'd be fine. We'll talk about how those are different in a second. F at x initial is something like maybe 1 plus 1 minus 3, or negative 1. F prime at x initial, you really should identify, in terms of good work, you should identify your derivative. As trivial as you might think it, you need to show your derivative in your work somewhere. So off to the side, would you please identify what you said the derivative was? In case there's an error, that's one place I'd look. All right, so the derivative at x initial would be 4 plus 3. Wait. So then if I solve this, I get something like 1 minus negative 1 over 7. My estimate is 8/7. Now you find that's actually a pretty good estimate, that 0, with just one iteration. Okay, you with me so far? Any questions? Okay. Yep.
Wait, how did you get this value again? It was just like,
Just trying to look at this. I tried x equal 1 because 0 is too small. I mean, x equals 0 is not bad. You get a negative 3 out, and that's pretty close to 0. 1 is a little closer. 1 minus 3, or 1 plus 1 minus 3 is negative 1. I'm getting closer to 0. 2 is too big. It's more like 16 plus 8 minus 3 is 21.
so the goal is just to get.
Yeah, you want to come out. It's nice to fence it in.
What does that mean?
Fence it in means you want to see a negative and a positive. I know the zero is between 1 and 2 because I went from negative to positive. I need 2. I'm just going with 1. First of all, because it's closer, but second of all, it's just
So it
easier.
doesn't have to be like exact.
So now that's a good question. I'll come to that. Good guess versus bad guess. I'll come to that back to that question. Okay? Yes.
Aren't there multiple roots that you can find?
So it depends on the problem, but yeah, you could get multiple roots, and depending on, let me just go there. I will talk more about this in a second, but say there are multiple roots, depending on your initial guess, you might hone in on one versus the other. If I tried this point here as my initial, despite the fact it's probably closest to that 0, it would probably find this one first. And so, yeah, depending on which one you want to find or how many you want to find, that also has to do with the initial. That's a good question. Okay? Exactly. I love that. All right, so here we go. I told you over there that Newton's method is designed to solve some really hairy problems. That these are called transcendental functions. They're not polynomial functions. They're not powers of x kind of functions. It can solve, or at least estimate really closely, these solutions. So, the first thing, as I told you a couple slides ago, Newton's method doesn't find intersection points. It finds zeros. So the first thing you must do is you must make it a zero problem to use Newton. So how do you make this a zero problem? Yeah, move everything to one side. It doesn't matter which side. And you're going to let that be f of x. And now you want to know where that whole thing is 0. Newton's method doesn't find intersections. Okay. Now, in terms of the calculator, would you, if you don't already have your calculator out, get your calculator out. This, you're pretty much going to generate a loop that your calculator can constantly do, and the work is nothing, and you can do 5 iterations just like that. Please put the function and the derivative in to your calculator. So 2 plus x minus shucks. X, is it x minus 2? Okay. In F2, would you also put the derivative? If it's a gross derivative, you can have the calculator, or if you're Rachel and you don't want to take the derivative by hand, you could have the calculator do the derivative by menu derivative, whatever. For those of us who don't mind doing the slightest modicum of thinking,
There's a better way, though.
is it better?
Yeah, no, go to the little thing with all the, above the multiplication sign.
Yeah. I understand the calculator takes the derivative for you.
No, but
The
there's
question
a
is really about Alzheimer's. Okay. It's been proven that a person that does routine calculations throughout the course of their life has a substantially less risk of Alzheimer's.
I'll be dead by that.
You think so? I'm going to come laugh at you when you have Alzheimer's. How
I
about
think
that?
maybe like 47. I think
47 you're going to die? I think
Yeah.
you'll change your mind when you're 47.
No, I think that you'll be dead by the time I'm
Oh, no.
old enough to have Alzheimer's.
Oh, no. I'm going to live forever. I do lots of calculations. Whoa.
Yeah.
Minus 1 divided
No, I
by...
think 47 is the time for me.
No, 47 is a great year. I'm 47.
What?
I'm 47. You saying I should die? Just give it
No.
up?
It's time for me.
Wow, that's terrible.
Just
What the heck happened? You got me all distracted. I guess now I'm proving your point right
yeah,
now.
you are.
I didn't actually choose the function. You can't actually type in cosine
Yeah, you
apparently.
can.
No, you
Put
can't.
in parentheses.
Oh, yeah. All right, here we go.
I think we took a
Are you you have the function in? Sorry, Alzheimer's discussion off to the side. Okay, now to get the whole process rolling, you need to start by storing your initial seed value into X. So we decided we were going to use. Did we even say? Let's use our graph for a good look. There are actually lots of zeros. We're just going to find one. Let's go with a guess of about 5. Okay, you follow? Actually, I guess we could, which one do you want to find? This one or this one over here by 10? They said start at 3? Oh, I'm sorry. Okay, great. So we'll start at 3. The tangent line then would be a visual of going like this kind of deal, right? Okay, so in terms of the process, this is what you do in your home screen. You store 3 to X. Store is right here. I'm sure you all know how to store stuff. 84 or Inspire, it's the same deal. You start the process by storing 3. Are you with me? Okay, now Newton's method then is to take the previous value, which was X, minus the function itself, which I have in F1 at that X, and divide by the derivative, which I have in F2 at that X. Now don't hit enter because I want to calculate that, but then I want to store it to X. I want to store over my old X with this new X. So you're now going to store that to X. It's going to take your old X, make this calculation, and store over your old one. My new estimate is 4.075. Now your calculator's got that in its mind. If you now just hit enter again, it'll redo that same thing, but with your new X. Now, keeping track of what you got going on here, this is X initial. This is your seed. This is X1, X2. I don't know what I asked for. Did I ask for 3 iterations? Okay, so one more, 3 iterations, and boom, there we go. Now, in terms of, because you're using your calculator a lot, the question is, all right, what do you need to show? This is what I want you to show. I want you to show, first of all, what your initial was, even if it was told to you. I want you to show at least one demonstration of Newton's method. So, for example, x1 is x initial minus f at x initial over f prime at x initial. And I want you to record that, which was 4.075-ish for the first iteration. Is that correct? 4.075. After that, I just want you to record the results of the other iterations. I don't need the formula. So x2, the second iteration was 4.508. And the third iteration was or is 4.676. All right, and that's to do 3 iterations, so that's our estimate. We should all agree on that estimate, assuming we used all the same C value. You with me? Did you get that?
Yes.
Okay, now, the question is seed value choosing. There are better seed values than others, and some cause you to take quite a while to get there, but there's actually only one really terrible, can't do it kind of choice. Imagine this curve and you're trying to find the zero, which you can obviously see is over there. What's the worst possible choice that would cause the whole thing to break? But a maximum, yeah, if you pulled a tangent line off of a maximum, give me one visual reason why that breaks it. Because it'll never touch the axis. It's parallel to the x-axis. Give me an analytical reason. Give me an analytical reason. Look at this equation and tell me why you've got a problem. Yeah. If you choose a seed value that has a zero derivative, the whole thing breaks down because obviously it won't have a zero at all. So try not to choose a horizontal tangent. Choose an x initial where there is a horizontal tangent. Okay. Other than that, it should work fine. It might just take a few, but if you have your calculator, it's no big deal. Last but not least, this is the hardest. Executing Newton's method is super easy. The hardest part of this is the first step in some problems, depending. Problems like this are the easiest kind. It's already set up. It's equal to 0. You know exactly what to do. The hardest part is where there's some ambiguity as to what do I find? What is even the equation? I don't even know what the equation is. You could use Newton's method to do a ton of estimating. Like if I wanted to estimate the cube root of 5 using Newton's method, it could do that, but you have to do some tweaking to the question to make it a Newton's question. Newton's only finds zeros, and it needs to be a nonlinear equation set equal to 0. So what do I do? Cube root of 5, make it a 0 of a function question. Let's go here. Cube root of x, or cube root of 5 equals something. I don't know, yeah? Maybe it would help to say equals something, so let's call that x. Now that's a start. Now usually there's 3 different ways people go from here trying to get there. They might say, all right, so what about cube root of x equals 0? That's not awesome because it doesn't have anything to do with 5, right? I mean, it's going to be 0. There's no guessing. I wonder what that is. We know what that is. It's 0. So this doesn't get you anywhere. We know this is 0. No 5 in there. So that's a good idea. You're getting the cube root idea and the 0 in there. And that's good, but it's not getting me anywhere. What else? Okay. So that's where we're going to head, and I'm going to go there. Another guess, I'm going to start with the other bad ideas, to move that over and set it equal to 0. Now that's logical because you're taking what they gave you and making it a 0 problem, right? The problem with that is it also doesn't really get you anywhere because, while you could easily choose x is maybe 1 or 2, you know what I mean? It wouldn't go anywhere because the derivative is just 1. In essence, really what you're doing is taking, what kind of function is this? It's linear. You're taking a linear function and putting a tangent line on top of it. It doesn't do anything. So it doesn't get you anywhere. The best is to take this and switch it around a little. So instead, think of it as, this really is what times itself 3 times equals 5. What's another way to say what times itself, or some unknown times itself 3 times equals 5? X cubed equals 5. Now that's getting somewhere because that can then be taken to a nonlinear, zero-y kind of problem. If I answer this question, then I'm answering that. Okay? So if I were to do that, I would take a seed value. We'll just do one iteration and call it good. What initial guess would you use? 1 or 2? 1, okay. 8 versus 1. Let's use 2. I think it'll be closer. But you could use 1 or 2 would be justified. Okay. X1 is x initial minus f at x initial over f prime at x initial. That is 2 minus, what is f at x initial? 8 minus 5 or 3, right? Okay. F prime, if f is x cubed minus 5, then f prime is 3x squared. F prime at x initial is f prime at 2. So I'm thinking something like 2 minus 3 over, well, yes. So 2 minus 1/4 or 1 3/4. Oui. Now I'm curious to see how good that is. Our answer is obviously 1.75. The fifth root of 5, or the third root of 5, is 1.71. It's pretty good. 1.75 versus the true of 1.71. Both in 400s. That's pretty super good, right? I think you'll agree it beats the heck out of the old school method to say, well, let me try 1.7 times itself and see what that is, and then 1.8 times itself and see what that is, and then you go to the hundreds in there. That's tedious. So this is pretty good. Okay, I don't really have time to go over the test. We'll go over that tomorrow. So let's go to questions on 92. Questions on 92.
No.
14?
I said 14.
14? That doesn't mean anything.
Yeah, 14.
14. 14 digit.
14.
14. Otras.
On number
12. 14, 12.
I know. Oh my god.
25.
My children are starting
Okay.
to.
I drove like 4 hours last night. Which was
My
You were
children
in the game, did you say?
definitely starting
I
to.
didn't say a lot more.
It was, I think they're best because
Really?
they only roll out one team and not the other.
Really?
So, I don't know.
Paul, can you vouch for that? Were the refs terrible? What?
This one was a bit weird.
Really? Like,
Normally we can play around them, but they were actually there.
they were actually that bad. That's too bad. That's a bummer. All right. Number 14. Here we go. 14 is a bit of a mess. But this is a good keep it organized question. It's also a good practice on a couple different skills, which makes it valuable for the big picture of things. Okay. It's important when they give you something that you use it to the fullest extent possible. And if you fail to use it to the fullest extent possible, then you will not get through. So, for example, when they say there's an inflection point at 0, -3, that needs to be used two ways. All right? One is because it's a point on the curve. That tells you that -3 equals 0 plus 0 plus 0 plus c. That right away says c is -3. We can conclude c must be -3. But you can use that another way. Inflection points happen where second derivative changes sign. Now the second derivative could actually change signs at either a 0 or an undefined place. But for a polynomial, there is no undefined place. It's just where it equals 0. So I would say f double changes sign means that f double must equal 0 when x is 0. You need to make, that's a bit of a leap. That's the hardest part. From that, I could say the first derivative is 3x squared plus 2ax plus b. The second derivative is 6x plus 2a. Now this fact. The second derivative has to equal 0 when x equals 0. The second derivative doesn't equal negative 3. That's a common mistake. Negative 3 is a point on the original curve, not the second derivative. So we'd say the second derivative is 0. That implies that a is 0. It's probably a good form to change as you go before you get too far in, putting what you know so that the rest of your life is easier. I could boil this down to x cubed plus bx minus 3 at the inflection point stage. Now we need to find b, the average value part. That's going to take a little more work. They tell you the average value on 0 to 4 is negative 1. Using that, f at c is the average value. So f at c is negative 1 equals 1 over 4 minus 0, 0 to 4 of x cubed plus bx minus 3 with respect to x. All right, so here we go. I'm going to move that 4 over there and anti-differentiate 1/4 x to the 4th plus b over 2x squared minus 3x from 0 to 4. That feels all right. Negative 4 equals 1/4 of 4 to the 4 would be 4 cubed, which is 64, plus b over 2 times 16 minus 12. All of that minus what you get when you put in a 0, which will just be 0. All right then. That means negative 4 equals 52 plus 8b. 8b therefore is negative 56. So b is negative 7. From that, for part A, I can conclude that f of x is x cubed minus 7x minus 3. Part B, then, is find a number in the interval 0 to 3 guaranteed by the mean value theorem for derivatives of the function. So I'm supposed to find a c guaranteed by the mean value theorem. All right, first of all, is f continuous on the closed interval 0 to 3? Does that cube go continuous? Yes. Does the derivative exist at all points in the open interval 0 to 3? Yeah, the derivative is continuous too, so it's fine. Therefore, by MVT, there is a c in 0 to 3 such that f prime at that c equals f at 3 minus f at 0 over 3 minus 0. And we're supposed to find the c. So here we go. What's f prime at c? I'll give you a second to catch up. So, what is f prime at c? Maybe you're good from here. I don't know. Maybe c.
Good morning, Devlin. John
C squared minus 7.
Pledge of Allegiance. Ready? Begin. I pledge allegiance to the flag of the United States of America and to the republic for which it stands, one nation, under God, indivisible, with liberty and justice for all.
Okay.
All students, course registration materials will be collected today during the 7th hour. Please report to your first period teacher for 7th hour and bring your course selected summary sheet with signatures from you, your math teacher, and a parent. If you're signing up for an AP class, you also need to complete an AP contract from the counseling office.
The Scholars of the Month were selected by the Electives Department and are as follows.
Ellen Florax says,
Yay!
Senior and musicians produce their best effort every minute of every rehearsal. Be Because of Ellie's dedication to the concert choir and her encouragement toward other singers, many students have improved their musical abilities and level of confidence. DHS has been proud to have Ellie represent our school at the Colorado All-State Choir for the past 2 years.
Harrison Zodiac is a sophomore in concert choir. He is a notable member of the concert choir because of his musical talent, enthusiasm, positive attitude, and willingness
Okay.
to help others. His charisma on
12,
is evident.
don't worry if your answer's slightly different. They'll be different by virtue of C.
He even sings in the sound of the Rockies Barbershop Chorus with men from all over the metro area.
Autumn Davis is an excellent music student, but what sets her apart in the classroom is her maturity and unflagging work ethic. Her enthusiasm and eagerness for knowledge is evident in everything she does in class. She is a great team player, and her love of music and excitement to accomplish wonderful things rubs off on everyone around her.
William Groff is new to the junior high choir and has been a tremendous addition to the group. He sets a great example for other students. In addition, he is always excited to sing and does a marvelous job reading music and singing harmony. His enthusiasm is contagious, and his great effort has contributed to the positive environment in his class.
And KHS will be selling Dairy Queen blizzards in the lobby after school tomorrow. Celebrate the warm day with a blizzard. We will have gluten-free and nut-free options.
XBA shirts are in. If you order one, you bring $10 on Friday. There are extra shirts available.
Students, don't forget to sign up for the first annual cupcake baking competition. Make over this weekend and bring 3 of your best in on Monday for the judges. Information sheets as well as sign up at the financial office.
Don't forget to check out the Artist of the Month, Tori Williams. Come check out her work in the counseling office.
Tomorrow is Career Exploration with guest speaker Dr. Lena Kulkarni Politano, who is a Dublin graduate. She received her Doctor of Dental Surgery and completed a 3-year orthodontic residency. She was featured in 5 to 80 Top Dentists and Extraordinary Women of Jefferson County. Please visit Library Commons.
There will be a girls' memory meeting tomorrow. It's tie-dye, so don't forget to bring something today.
The Denison Elementary School PTA scholarship application is available in the counseling office for seniors. Deadline April 15th.
Glennon Heights Elementary School scholarships for seniors and teaching any student can apply if they
Okay, 25?
even if they did not attend Glennon Heights.
Senior high students. Youth Leadership Jefferson County is an innovative program to develop the leadership potential of high school students while building a deeper understanding and appreciation of their community. Each full-day monthly session focuses on an aspect of the community, including government, business, health
Now,
service.
because it's in a hemisphere, that means the height has to be equal to the radius.
Junior guys, do you have what it takes the nation's career program to develop
So
smart
the
leaders
surface
that will
area,
apply for the 2018 American
I'm not sure if you
Colorado
remember the
State
code
Program?
surface area, but it's
Free
pi r
people
squared for the
can
base,
call money experience and
plus
operations
pi r L
software
for the side.
of government.
That was the slant height.
Yes, in Colorado Springs in June.
I don't know if they wanted to relate it there or find out. If you found L, it would be the square root of
American Legion Colorado Girls State Program is an
something
exciting
like
government in action learning program to which is
root
attended.
2R.
Program is held at UNC in June. For further details, see counseling.
So I don't know if they asked you to find that or not.
Junior high students that are planning to attend the city event on Friday, March 9th, you need to turn in their permission slip by tomorrow, Friday, March 2nd. You can turn in your permission slip at the front
The
office.
volume in terms of R only
It's turn in your permission slip
would be
on
1/3 pi R cubed because R is in.
That is all your announcements. Have a great day.
Anything else? Okey doke. Right,